In this video, I want to show you how to do a scan using the mod redundant feature in GaussView. And so in this case, I want to scan the HOH bond angle in water and look at how the energy changes as a function of that. So there's several different ways you can do it, but one way you can do this is with this redundant coordinate editor. So I'm going to come up here, I'm going to click the redundant coordinate editor, and it's going to open this window. And actually, before I do this further, I want to come back to my molecule. I'm going to right-click here in the window, do View Labels, and now I can see the labels of the atoms. So these are just the order in which the atoms have been placed, 1, 2, and 3. But when we're defining our redundant coordinates, we're going to be using these numbers of the atoms in the order they were placed. So I'm going to add, come up to my redundant coordinate window, click Add. Right now it's an unidentified one, but I can go ahead and select an angle from that option. There was some graphical glitch, so the menu options weren't showing, but it should work fine when you do it. And now I need to pick my atoms, so I can do atoms 2, 1, 3, and then I'm going to come here and I want to do a scan coordinate over that angle. So I've defined angle 213, which is my HOH angle, and I want to take, say, 6 steps of 0.5 degrees. So, and in each one of these steps, we're going to allow it to do a little optimization to that angle. And if there were any other degrees of freedom, it would optimize them. In this case, we only have 3 degrees of freedom, so it's going to make that work. In older versions of Gaussian, you could actually set your initial angle here. I'm pretty sure that in the current version of Gaussian that feature no longer works, but it's still here in this GaussView due to a slight version mismatch. But I think you're better off just setting up the geometry in what you want as your initial geometry. So I'm going to leave it at this. I have an angle for 213 scanning 6 steps of 0.5 degrees. And now we have that. And now I'm going to just make sure that the angle we have is one I like. So maybe I will go ahead and start us at 103 degrees. And so we'll be scanning 103 up to 6 more steps beyond that. And I think that may also include 1 step at the initial geometry. So I think we may end up at a total of 106.5 degrees. Now let's go ahead and set up our calculation. You'll notice even just by opening that and setting up that redundant coordinate thing, it automatically set us up for doing mod redundant type optimization, which can include a scan. So this is setting us up for the scan based on the things we set there. With it relax, meaning it's going to be relaxing all the other degrees of freedom except for the ones we're scanning. And then we can just go ahead and set our method. We still have, from an earlier job I had done, it was set to B3LYP in the STO3G basis, charge 0, spin state singlet, and so on. We're going to go ahead and leave it like this. Just to let you see how this all looks, I'm going to open up the window to edit it. I'm going to save this again as test.com. And you'll notice, so here is my input file, and down here is the information is added about the scan. Though actually I'm a little concerned also that we may need to turn off the connectivity information. I'm not quite sure if that will be compatible. So for safety in a moment I'm going to turn that off. But the main thing here is we have our molecule and we have the A, meaning it's an angle. This is our mod redundant coordinate for atoms 2, 1, 3. S is for scan, 6 steps of half an angstrom each. So you could use the redundant coordinate editor to create these, but you can also create these sorts of things by hand if you know what it is you want. You can learn the format for these, and it's basically the type of coordinate, the atoms involved, and of course the atoms involved will depend. If it's a bond, it's just 2 atoms. If it's a dihedral, it's 4 atoms. If it's an angle, it's 3 atoms. Scan, how many steps, and then the step size for those steps. I'm not quite ready to submit this. I'm going to turn off the right connectivity information. If we go ahead and look at it again, you'll see that now that information is gone and we just have the scan. And the reason I'm doing this again is I'm not 100% certain, but I think Gaussian might complain if there's that right equals connectivity information or geom equals conductivity information in between the scan coordinates and the geometry. I think the scan coordinate information needs to be just after the geometry. Alright, so now I'm going to go ahead and submit this. This will take a little bit longer because it's going to be doing a series of several geometry optimizations, one at each of our scan points. But luckily it's a small molecule, so it was pretty fast. We can go ahead and look at the results, and we get this. And so here's our molecule. I took out the conductivity information, and I guess it decided to delete it entirely. I'm going to set these back to being single bonds just for the sake of the pretty picture. And we can look at the different geometries. I guess you'd have to manually turn them on for each thing, but you'll notice that the bond angle is changing slightly. If I measure, for example, this one's 104.5. This next one should be 105 degrees. Oops. And so on. And notice we have 7 total geometries because it did, the first one is 103 degrees, and then it did 6 additional steps of half an angstrom or half a degree each to end up at 106. We want to see the energetics for this. We can come up here to the results and scan window, and you'll see the plot it made of the scan. Here's the energy. It is not so interesting, I guess. Well, we know the true energy minimum is for the optimal angle is somewhere around 104.5. And this cheap little calculation I ran, it's clearly would actually prefer slightly narrower geometry. So it's even saying the minimum is somewhere below 103 degrees. So if we wanted to see a minimum for that, we'd have to scan even through some shorter bond lengths. But anyways, this gives you a basic idea of how you can use a scan to map out a potential energy surface along a particular reaction or geometric coordinate.